Hi everyone. In this lecture we will talk about an efficient quantum search algorithm called Grover's algorithm. It's one of the major quantum algorithms developed by Love Grover in 1997. It's also one of the most practical quantum algorithms in literature, and it concerns unordered search problem, or it can also be thought of as searching an index or a key value through an unordered database. So classically speaking, we can solve this unordered search problem in an unstructured list or a database in n many steps, where n is the number of entries. So if we have n many entries in an unordered list, then using classical computation, we can solve this problem and suppose that we have only one key value that we're trying to find. Then we can solve this problem in at most in the order of n. Okay. In big O n steps. Precisely in n minus 1 steps. Because if we search through all the entries and if we can't find up to the last entry, then we know for sure that the key value will be in the last entry. So we really need to search through n minus 1 entries. But let's say it's in the order of big O n. So we can solve this problem in linear time. Okay, linear time. Now Grover's algorithm is a quantum algorithm which solved this problem in square root of n steps. So we have a quadratic speedup over the classical algorithm. Now, one way to put this problem is we should put this problem in an abstract form. We consider a function given as a black box So now we're trying to state the search problem in terms of functions. Now suppose we are given a function f from 0, 1 to the n to 0, 1, such that f of x is equal to 0, but for 1 x star f of x star equals 1. And the problem is to find this key value. Find the key value x star. So x star is the entry that we want to find in our unstructured database. This can also be translated into this problem. Let's assume for convenience that we have n is equal to power of 2, and let's say that we have n many entries, and we want to find a key value x star in this n many entries. Okay, and we're assuming for the moment that we have only one key value that satisfies this functional property. Of course, if our list was structured, if it was ordered, then we could solve this problem more efficiently than linear time by using binary search, for instance. To obtain a more efficient solution, and we could solve this problem in logarithmic complexity, in fact, using binary search. But in the worst case scenario, if we have an unstructured list, then the complexity will only be a linear time. Okay. So how can we solve this problem using quantum algorithm in square root of n steps? Well, the key step is to, there are two main steps in solving this problem. The first step is to separate the key value from the other values, okay, and then play with the amplitude of the key value. Now, suppose that we are given a quantum oracle Okay, so this is actually the quantum version. The quantum version of f. Okay, f is given as an oracle, and O denotes the quantum version of f. And O is simply defined as, it takes two inputs, ket x, and the oracle control qubit q, and it maps to x and q XOR f of x. So here x is the index register such that x is an element of 0, 1 to the n, and q is the oracle qubit. It's a single qubit. It basically controls the index register. Now, as our first attempt, let's try to put all entries, okay, all inputs of x in an equal weighted superposition. Okay. So that means that we have all combinations of strings of n bit length, each with the amplitude 1 over square root n. Okay. Put all inputs in a superposition. And so we get 1 over square root n, summation x. X is a member of 0, 1 to the n, x. And let's set the control qubit to 0, okay, ket 0. All right. Now, if we apply the oracle O to this input, then we get we simply get 1 over square root n summation x f of x. Since q is 0, q XOR f of x is simply f of x. So what we now hear is now all index values, all entries in our list is put in a superposition of equal amplitudes. Okay, so suppose that we have entries 0, 1, 2, We have n many entries, so up to n minus 1, each with amplitude 1 over square root n. Okay? This represents the amplitude, and this represents the basis state. All right. Now, if we measure the first register after applying the oracle, it will return us one of the n many strings. It will return us one of the n strings with equal probability, right? 1 over n. And measuring the second register will give 0 with probability, actually. So measuring the first register will give one of the basis states, one of the n many basis states. And measuring the second qubit will give ket 0 with probability n minus 1 over n, or it will give 1, ket 1, with probability 1 over n. So the chance of observing ket 1 upon measuring the second register is only 1 over n. And since the first register and the second register are entangled, if we measure ket 1 in the second register, then that means that we have found the key value. But this is very unlikely. So as n grows, the probability of finding the correct key value gets very low. Okay? So we need to find a better solution. And there are two tricks basically in Grover's algorithm. The first trick is called the phase inversion step. So two tricks. First is the phase inversion. Phase inversion of the key value x star. So what does that mean? Well, roughly speaking, that means we want to mark the key value by changing its phase, by flipping its sign. Okay? And it works in the following way. We set the oracle qubit, the control qubit, in the negative phase superposition state. Okay. We set the control qubit of the oracle O to ket 0 minus ket 1 divided by square root of 2. That is basically equal to Hadamard 1. Right? So then the action of the oracle then becomes, remember that if the second qubit, if the control qubit of the oracle is the negative phase superposition, then in fact it acts as an eigenvector, because this superposition state, the negative phase superposition state, is an eigenvector of the oracle. So if we have x in the first input, and if we have 0 minus 1 divided by square root 2 in the second input, then it will map to minus 1 over f of x tensor ket 0 minus ket 1 divided by square root 2. Now, to simplify the action of the oracle, we can actually omit the second qubit of the oracle. So the action of O could be rewritten as x maps to minus 1 f of x, x. Oh, actually, I forgot to put x here, so we have ket x here, okay? All right, so then depending on the value of f of x, if f of x is equal to, if x is equal to the key value x star, then f of x star will be equal to 1 by definition of the function here, right? So then we have minus 1 to the power 1. So then the amplitude of the key value x star will be flipped, will be negative, and all the rest, all the amplitudes of the other values, which are non-key values, will remain positive. So this oracle helps us to separate the key value from the other non-key values. Okay, so how does the phase inversion act on concrete states then? Let me give a small example to illustrate this. Suppose that we have 4 basis states. Okay. So example. Suppose we have a 2-qubit state. That means we can represent 4 basis states, 4 different basis states, and assume for convenience that we start with an equal superposition. If we put all inputs into superposition, then we get 1 over 2, 1 over 2, 1 over 2, 1 over 2. Now, assume that our key value is, suppose that we're trying to find the basis states. Ket 1, 0, okay? Now, after performing the phase change, okay, if my key value is equal to 1, 0, state 1, 0, then after applying the oracle, my new state will be applying O will produce 1 over 2, 1 over 2, minus 1 over 2, 1 over 2. So it leaves the rest of the states the same, but it flips the sign of the basis state 1, 0, which is our key value, the value that we're trying to find. Okay. But measuring this state, the new state, let me denote it by psi, measuring this new state will give us one of the basis states with equal probability. So this is very ineffective. Somehow we want to measure the basis state 1, 0. We need to pick this up, okay? But how can we do that when all the amplitudes are the same? So that's why the second trick of Grover's algorithm is called inversion about the mean. So somehow we need to amplify the amplitude of the key value. We need to amplify the key value, amplify the amplitudes of the key value. And we do this by inversion about the mean. So second trick, inversion about the mean. What I mean by this is that we invert the amplitude of all states around the average amplitude. So let's consider, for example, a sequence of integers say 53, 38, 17, 23, and 79. So the average of these numbers, let me denote it by mu. Mu is equal to 42. Okay, 42 is the average. And if we want to invert an element alpha around 42, then the new state of the element will be alpha prime, which will be equal to mu plus mu minus the original value, right? And this is equal to 2 times mu minus alpha. So if we are given a general state, a general superposition state, given a general state alpha k, k, the inversion about the mean will change the amplitude of each state, and it will produce summation k 2 mu minus alpha k ket k. Of course, mu here is the average of all amplitudes, where mu is equal to 1 over n times summation of all alpha k's. All right, but we need to apply this inversion operator, the inversion about the mean, in terms of unitary matrices, okay, because quantum computation consists of unitary transformations, and we define transformations using matrices, particularly unitary matrices. So how do we apply this inversion operator using a matrix? Now, I'm going to give another example to demonstrate this. Suppose that we have a vector having these numbers here. So suppose that our vector consists of 5 elements, 53, 38, 17, 23, 17, 9. Okay. And consider the matrix A, which a 5 by 5 matrix, which consists of all 1 over 5 as elements. 1 over 5, 1 over 5, 1 over 5, 1 over 5. Now, if we apply A on vector V, so AV will return 42, 42, 42, 42, and 42. It's actually going to take the average of all amplitudes, average of all numbers in the vector. Okay. And in terms of matrices, the formula, the average formula here, okay, then becomes, let's call this, okay, so the new value after the inversion two times A times V minus V, but that's equal to 2 times A minus the identity matrix times V. And the situation doesn't change if we worked with 2 to the n many elements. Then our matrix, average matrix, will consist of, will be a 2 to the n by 2 to the n matrix consisting of 1 over 2 to the n as its entries. If we had 2 to the n many elements. Okay. So then this operator, 2a minus I, inverts the given vector about its mean, about the average. But then how do we implement this using unitary transformations? Well, first we need to define an n-qubit operator. Okay, what we need to do is that we want to first apply an inversion around the state 0, and then apply a change of basis operator. Okay. After the basis change, we apply the inversion around 0, okay, and then change the basis again so that it looks like as if we applied an inversion around the superposition state. Now, what I mean is as follows: if we want to apply an inversion around the general superposition state, okay, which will constitute as the inversion around the mean, what we could do is that we could apply the inversion around, first what we could do is that we could change the basis to a general superposition state. Then apply inversion around cat 0, okay, And then again change the basis. So that is, we revert the process. But then it will look like we changed, we applied inversion around the general superposition state. Okay? So we use this quite often in quantum algorithms. First we change the basis, apply some operations, some unitary transformations, and then revert the basis back to its normal state. Okay, back to the normal basis. All right, so how do we implement an inversion around the state ket 0? So we can think of this inversion operator for n qubit states. So we generally want to invert the state around the 0, 0, 0 states, n many. Okay. So what we really want to do is that inversion around 0 tensor n. Okay. So our operation will be denoted by u0 perp. Okay. So u0 perp will be defined as it maps x to minus x if x is not equal to 0, and it maps 0 to 0. When I say 0, I mean 0 tensor n, okay? I should maybe make this bold to explicitly state that we're working with n many qubits. Right. So it maps 0 to 0. It leaves 0 as the same, but it leaves anything. But it maps anything else to its to the same state with the negative phase. It maps x to minus x if f as long as x is not equal to 0. All right. So in terms of matrices, we claim that this inversion around 0 is equal to 2 times the density matrix of 0 minus identity matrix. Okay. And this is simply equals to, this is equal to 1, 0, 0, 0, and then we have 0, minus 1, 0, and then we have 0, 0, minus 1, 0, and then we have 0, minus 1. So this matrix actually inverts the phase of the states that are orthogonal to. So let me write that down. Inverts the phase of all states that are orthogonal to the 0 state. Okay, so, and as I said, but we want an inversion around the general superposition states. And the reason why we want to do that will become clear, because inversion around the general superposition state will correspond to inversion around the mean. Okay. We really want to do an inversion around the general superposition states. One over square root n summation k ket k. And as I mentioned earlier, we can simply do this by transforming this superposition state psi to all zero states. And then now that we have done a basis change, we can do an inversion around 0, and then again transform the basis 0 back into psi. Okay. Now for this we define the operator for this basis change. Okay, so I think it should be clear that what we're doing here, we want to transform psi into all zero state, and then do inversion around all zeros, and then change the basis, all zeros, back to psi. So it looks like as if we did an inversion around psi. Okay. So for this purpose, we define the operator h times u perp times h. This will do the job. Okay. So claim is that h u0 perp h is actually equal to 2 times projection matrix of psi minus I. Okay, so the details for this is in the lecture notes. Okay, so check the lecture notes and make sure that you understand this. But actually, this matrix, this h times u0 perp h, is equal to something like this is equal to the matrix 2 divided by n minus 1. And along the diagonal we have the exact same value, 2 over n minus 1. And everything else is 2 over n. Okay, but along the diagonal we have 2 over n minus 1. So this matrix inverts the given vector around the mean. okay? Because if you multiply this vector with an n-dimensional, if we multiply this matrix with an n-dimensional vector, then if we multiply this matrix with a given vector, say alpha 0, alpha 1, alpha n minus 1, an n-dimensional vector, then the outcome will be well, each entry will be equal to 2 over n summation y from 0 to n minus 1 alpha y minus alpha x. And this is exactly what we wanted.